All right, let's get started. So very happy to have Tom Hartman to tell us about coarse graining, pure states, and AdS CFT.
Okay, thanks a lot. And thank you to the organizers. This has been a really great week so far. So I'm going to tell you about some recent work with Jivan Chandra, who's a student at Cornell. So what I'm going to tell you about comes in two parts. The basis for it is a class of Euclidean wormhole solutions in d-dimensional AdS. So let me give the preview of what these solutions look like. These solutions can be used for various things. I'll describe one of them. But here's the kind of solutions. So these are solutions of Einstein gravity plus matter in d dimensions. They're Euclidean. They have k boundaries on which we place the flat or round metric. And they're supported by matter. All of the solutions that I'll discuss are spherically symmetric. So think of this as just the R and Euclidean time directions that I'm drawing here. And each point on this diagram is a sphere, except for the edges here. These are not true edges. That's just the pole of the sphere. I'll mostly discuss the case that is cyclically symmetric by rotating the k boundaries. Although the solutions, there's no reason they won't exist if you break the cyclic symmetry. These kinds of solutions are generic. I'll discuss a couple different kinds of matter content, but I think that solutions like this will exist with just about any reasonable matter content, with one important point, which is that depending on what matter you pick, there'll be a maximum number of boundaries that you can have for these type of wormholes. And sometimes that maximum will be less than 2, in which case you can only have fractional wormholes with less than 2 boundaries, but those still make sense and we'll still have a CFT interpretation. There are other wormholes that are known in higher dimensional AdS. As far as I know, the ones that have been discussed required, so they don't have known CFT interpretations. The ones that I know of actually, if they had a CFT interpretation, would involve deforming the CFT. Whereas with the boundary conditions here, the CFT at time 0, which is like right here, has no sources turned on. So this is just going to be related to states in the ordinary undeformed CFT. These wormholes are more like the ones that have been discussed in the West Coast model in JT gravity. Well, in particular, if you take those wormholes and give the end of the world brain a large mass, then you get a similar set of wormholes. And there are wormholes that we studied recently in 3D gravity, which are also similar to these. Yeah.
I'm just curious, if you, is there a reason you picked the sphere, right? Instead of say something with a circle or something that would be a little bit weird to work with?
Well,
sure what the sphere
don't think of this as being related to the sphere partition function. Think of it as being related to states and radial quantization. It's going to be related to pure states, which are created by inserting operators on the sphere.
Okay, yes, you insert operators.
Yes, the matter shells are created by inserting operators in the CFT on a sphere.
So it's just very a bunch of spheres. It's a bunch of spheres with insertions.
That's right. That's where the matter shells come from. Some insertions. So this would be like I'll write it in a minute, I guess, but like think V dagger V to the K as the kind of boundary condition that we're talking about here.
Yeah. Okay.
So I'm going to start by describing these solutions in some detail. Then the application, I'm going to explain how these wormholes can be used to define a coarse grain density matrix. And then I'll conclude with a few remarks. Before I start, let me clarify some terminology. So wormholes, of course, are puzzling in AdS CFT because they don't factorize. And interpretation that's been mostly discussed is in terms of ensemble averaging. I'm going to make a distinction between ensemble averaging and coarse graining. Ensemble averaging, in my terminology, means averaging over theories or spectra or OPE coefficients, et cetera, with some measure that you decide or is determined beforehand. Whereas coarse graining is something that you do in a fixed theory to define observables in that fixed theory, and you try to define them in a way that's convenient to you. In particular, a coarse-grained observable is one that's insensitive to UV details, or at least certain UV details. And these are not two different. It's not that one of these has to be right and the other has to be wrong. It's just that these can often be two different ways of thinking about the same calculation. And I'm going to emphasize the coarse graining picture because that's been less discussed, but we could phrase it in this other language. So I'm going to be talking about observables in a fixed theory and how these wormholes relate to observables in a fixed UV complete CFT. Okay, so let me start by explaining these solutions in detail. The bulk theory, as I said, is, well, these kinds of wormholes exist for various types of matter, but I'll focus on two specific examples. The first one is Einstein gravity plus dust. So these are like the thin shell solutions that you'll find in a GR textbook. So dust just means a pressureless perfect fluid. The second set of solutions, examples that I'll discuss, is Einstein gravity plus end of the world brains. And for our purposes, an end of the world brain is just a particular type of matter. It's a somewhat exotic type of matter. There's a tension associated to that end of the world brain that shows up as a parameter in the action that you place on the brain. In the CFT, this will correspond to doing the Euclidean path integral with a boundary, and that'll create some state in the CFT. So we can just think of this as a particular type of state. Okay, so let me start by describing the black hole solutions, and then we'll go to the wormholes. The black hole solution is the K = 1, single boundary solution. So the black hole solutions that we're interested in are not mixed state black holes, but pure state black holes with some matter behind the horizon, which you can think of as like the star inside the black hole. So for the first example, the thin shell black holes, the way you construct these solutions is you start with the eternal black hole, and then you put a thin shell of matter chopping off part of the eternal black hole. So what I'm drawing here is the Euclidean time circle, and we're going to put the thin shell here and then glue that to global AdS. Okay, so we chop off the eternal black hole and glue that to a vacuum AdS region. And the way this gluing is done means that we're talking about pure states in a theory on the sphere or cylinder in the CFT. So although we started with the eternal black hole, which had this closed time circle, once you glue, the circle is no longer closed. So this is something that starts in vacuum down here. You evolve upward, you insert the shell, you insert the operator, which is a spherically symmetric operator that makes the shell, and then you jump over here and evolve in Euclidean time. And the shell is inserted at Euclidean time minus tau 0. And if we're calculating a norm, the dagger is inserted at plus tau 0. So if we think about the path integral for this black hole, then what it's calculating is v dagger, or in terms of these operator insertions, v of minus tau naught and v of tau naught. Okay, is that clear?
Sorry, Tom, can you just say what the Lorentzian picture is, that it's a one-sided black hole with the shell behind the horizon?
That's right, and it has this will be important later, but it has a shell behind the horizon already at time 0.
Yeah, because it's not an end of the world shell, right? There's on the other side of the shell, is that right? Because you're doing this gluing.
Oh, yes, that's right.
So what's on, it goes to argue, you go to
It's
argue
empty.
0. That's
Uh,
it, yeah.
Yeah,
Yeah, it's like a collapsing star that comes out of the past singularity and goes.
exactly.
Yeah.
That's right. Okay, so that's the black hole. And now we can construct wormholes by cutting and gluing copies of this black hole. So here's what we're going to do. We're not going to talk about the wormhole quite yet. We're going to talk about the quotient of the wormhole mod zk. So we're talking about wormholes that are cyclically symmetric, replica symmetric. So we chop off a piece of this wormhole. The red line again is the thin shell. So this is being glued to a vacuum region. I'm going to stop drawing all those glued vacuum regions from now on, but they're always there on the other side of the shell. So we take a piece of this pure state black hole, we chop it with an angle here 2 pi over k. And what that allows us to do is to glue together k copies of them into a smooth solution. Okay, so the picture that I've drawn here is for k equals 3. We take this wedge, this pizza wedge here that's been drawn, and we glue together 3 of them like that. And that gives us one of these geometries that I drew at the beginning. Now a case with 3 boundaries. A couple notes here. First of all, it's clear from this construction that there's a maximum value of k, because the bigger I take k to be, the more this wants to squeeze over to the left, and eventually it's going to hit the matter, and the picture will break down. Okay, so depending on what matter I pick to form this initial black hole, I'll be able to do this wormhole construction, but only up to some maximal value of k. Now, maybe you can go further, but not with a saddle point constructed in this way. Based on what we're going to see in CFT, I think to go further, you would need to be able to go off shell. So that's the first comment. There's a k max. The k max depends on various parameters. Like for the end of the world brane, it depends on the tension, depends on the space-time dimension. For the thin shell, it depends on the mass of the shell. The second comment is that we want to pick boundary conditions. This is a choice, but the choice we want to make is to pick boundary conditions corresponding to this correlator raised to the k power. And in particular, the correlator had operators inserted a distance plus minus tau naught from the time reflection t equals 0 slice. So we want these wormholes on each boundary to have operators inserted at plus minus tau naught. So we want this length here to be 2 tau naught, this length here to be 2 tau naught, and this length here to be 2 tau naught. In order to achieve that, you have to start with a black hole at a different temperature. Okay, so if your initial black hole has one temperature and you want to replicate it, then you have to pick a black hole of a different temperature and do this construction on it. And there's a boundary condition that relates the temperature of the temperature, whether it relates this k-dependent temperature to tau naught. Actually, writing it down is complicated because the relationship between beta and tau naught is complicated, but there's a simple implicit relationship that you can write, which is that boundary condition. So the picture that I just drew was a good picture for thin shell wormholes. For thin shell wormholes, let me go back. For thin shell wormholes, if you make the shell heavy enough, you can put it very far behind the horizon. So if I make a very heavy shell, I can put it way over here on sticking near the left side of the Euclidean diagram. The situation is different with end of the world branes. So the end of the world brane wormhole is constructed, the black hole and the wormhole are constructed actually in a very similar way. The difference is that this red line, instead of being a thin shell glued to global AdS is now the end of the space-time, and there's this extrinsic curvature term in the action. So again, the geometry is just one of these cut-off eternal black holes, but the equation of motion for this red line is different from the equation of motion for the thin shell. So it's just two different equations of motion, but otherwise the description is very much the same. There is an important difference for the end of the world brains, which is that the end of the world brain black hole, always the endpoints here are always like I've drawn. They always are over towards the right. Well, the best you can do is make them make the brain vertical. If it's tensionless, it'll be vertical. If you turn on some tension, then they'll always move to the right, which means that the end of the world brain black hole covers at most half of this thermal circle. And that means that when you try to do this cutting and gluing procedure, that you actually can't do it for any integers bigger than 1. Now, if we talk about the quotient wormhole, we can take k to be non-integer, and this procedure works perfectly well for k between 1 and something less than 2. That depends on the tension of the brain. So if you give me a brain tension, then I can construct wormholes with like 1.7 boundaries, but not with a positive, not with a real integer number of boundaries. These fractional wormholes make sense if you talk about the quotient geometry, and in fact are going to have a consistent CFT interpretation. So we don't actually need, for the coarse graining application that I'll discuss, we don't actually need the wormholes to have multiple boundaries. It's enough that they have more than one boundary. Okay, so now I'm going to discuss the CFT dual. There are different ways, as I mentioned at the beginning, of interpreting this. One is as an ensemble average, similar to what's been discussed in 2 dimensions, especially in this West Coast model paper, where you interpret these as the average calculation of v dagger v, this correlation function raised to the k power. Now, mathematically, you can do this. You can match these. There's a calculation you can do. I put a question mark here because I'm not really sure what this average means. There's some procedure where you expand this in energy eigenstates and you take a Gaussian average of the expansion coefficients that reproduces the bulk. But these are not real theories. We don't have an ensemble of theories to average over. So I think we're still learning what this bar means and trying to understand what this bar means. But if you accept that this is some ensemble average, then you can apply this picture to things like the Page curve, to the discussion of global symmetries in quantum gravity, and various other things that have been done in 2 dimensions. The difference here is that, at least with this construction, we only know how to discuss on-shell wormholes, whereas in JT, you can also discuss contributions that are off-shell. The other way of stating the duality is basically boils down to the statement that we can think of this wormhole that I've described as a replica wormhole, replica manifold for coarse-grained entropy in a fixed CFT. That's what I'm going to focus on for the rest of the talk. So I want to explain how we think about these wormholes as arising from coarse graining and what that tells us about coarse-grained states and coarse-grained entropy. So let's go back a minute. So we're sort of take a step back and consider it a new question. So let's consider a pure state black hole with matter behind the horizon at the initial time. So this is the black hole that I talked about before. In Lorentzian signature, this is a shell, as Daniel described, that's behind the horizon already at time 0. The t equals 0 slice here, which is time symmetric, looks like this. there's a minimal surface here, and there's a bulge behind the horizon supported by the matter. In this case, the minimal surface is also it's a time symmetric apparent horizon. So I might call it an apparent horizon, but maybe you prefer to think of it as an extremal surface. It's certainly a subdominant extremal surface in the sense of the Rutakyanagi formula, because we're talking about pure states. The von Neumann entropy of this state is 0. And the Rutakyanagi surface is the nothing surface that just contracts away to nothing over the end of this spatial geometry. On the other hand, it's natural to assign to this apparent horizon some kind of coarse-grained entropy. This has been discussed especially by Engelhardt and Wall and collaborators, which I'll come back to Engelhardt and Wall in a minute. But basically what I'm going to be describing is a different way of thinking about this coarse graining. It's another way of assigning a microscopic formula to the coarse grained entropy of this horizon. The two are compatible. It's just another way of assigning a density matrix here. So what we're looking for is some kind of coarse graining map where we start with a pure state rho and we construct a coarse grained density matrix rho bar whose entropy is the entropy of this subdominant extremal surface. So let me go through this strategy, and this is probably the most important slide. Okay, so I'll ask me questions if there are questions, and I'll go through this carefully. So here's the strategy. We want to use wormholes to find the coarse grained density matrix. That's the goal, and this is the strategy to do it. Okay, so given a pure state black hole rho, step one is to find the replica wormholes that branch around the apparent horizon. Okay, since there's a minimal surface there, by Lefkowitz-Malesena, we can certainly branch for k near 1. They've already given us that solution. All you need there is a minimal surface. That construction does not care if it's globally minimal or just locally minimal. Yeah.
So Engelhardt and Wall define the coarse graining. I mean, you have to sort of say what you're holding fixed, right, when you're doing the coarse graining, and they were holding the outer wedge fixed.
I have a slide on that, on the comparison in a minute. It's the next slide.
Do you mind saying anyway just what defines the coarse graining? Because I think
yes, that's what I'm doing here.
Strategy, if we understand what's being fixed.
Yes, that's the goal here. Yeah. Okay. Okay, so we can find replica wormholes that branch around the apparent horizon. From the way that I've described these wormholes in part 1, those are clearly the wormholes that branch around this apparent horizon. Because if we take the k to 1 limit of this quotient construction, then we get back Lefkowitz-Malesena. So those are the replica wormholes for this apparent horizon entropy. Now step two is the tricky one. So step 2 is to find a density matrix in the dual CFT that reproduces the wormhole. So if you're able to do that, and I don't have a general procedure for that, but this is something that we can do in the examples that I described. If you can find a density matrix in the dual CFT, rho bar, that matches the wormhole, then we'll call that the coarse grained density matrix.
Sorry, Tom, that's a pretty rough. I mean, for example, I could conjugate rho bar by unitary, and it would
yes,
still give the same.
That's right.
Okay, yeah, that's how you said there. Okay.
Yes.
I mean, so but that's a pretty. I mean, that would differ.
That's right.
I think that's not what we'd usually call coarse. I mean, usually coarse graining is not invariant under unitary
Well,
conjugation.
I think it's like Raphael said, that when we coarse grain, we have to decide what we want to hold fixed, and the choice that I made. Well, think of the goal in life of rho bar is to give us a microscopic formula for the apparent horizon entropy. That's its goal in life, and I'm going to choose to do a coarse graining that has the correct entanglement spectrum. That's the definition of this coarse graining, And so it matches the entanglement spectrum. And then it's necessarily gonna give us a formula for the coarse grain
I
entropy.
mean, I would have felt like coarse graining should, for example, not mess up the 1-point function of the stress tensor or something, right?
This will mess up the
This
1
will
point
definitely
function.
mess that up,
I'm
right?
not sure of the stress tensor, but other 1 point functions.
Yeah.
That's fine, but
Yeah.
okay, coarse graining is there isn't like one way to coarse grain. We're defining a coarse grained object, which is designed for a specific purpose. And in this case, the purpose is to be able to write the coarse grain entropy of the
Maybe it should be
horizon.
called, I don't know, maybe, okay, maybe we're just fighting about words, but to me, coarse graining means that you should agree with the sort of trivial, simple observables. You know, like that's what it means in statistical mechanics. Maybe it means something different here, and that's, I guess it's okay, but.
Okay. Yeah.
Tom decided that the simple observables are the spectrum of the density matrix.
Yes.
Yeah, I mean, I can't, yeah, that's fine.
Yeah.
I mean, okay.
This is sorry, what's the question?
Was it important that wormholes appear in this slide, or can you have discussion for just connected versus disconnected?
Oh, yeah, I suppose one could do something similar for that case. Then you're going to have to, it just feels more complicated because there won't be different boundaries. And well, part of the point here is that we're going to get a nice simple formula for rho bar. This is not something you can do with like the Engelhardt-Wall coarse graining. We're going to get a nice simple formula for rho bar. I think you could apply a similar procedure to the transition that you're talking about. It's a little more complicated because it's UV divergences and you might have to talk about the modular Hamiltonian instead of the Hamiltonian, but I don't see why it would be terribly different.
I mean, morally, I thought you kind of do get a rho bar from Engelhardt and Wall because they have this this awful word minimar or whatever, but there's some they have this construction where you double to the other side using CPT and they construct some
Morally,
explicit state.
yes, but I'm going to write a formula.
Well, I thought that kind of is a formula.
Maybe you can write a formula, a CFT formula.
Yeah, so theirs is a bulk construction, and then you have to decide that every bulk
Yeah.
state has a CFT. Yeah,
Um,
that's true.
Engelhardt and Wall is a value structure.
Yeah.
Yeah, my goal, I mean, there are different things we could use coarse graining for. And the one I would like to use this for is to write a CFT formula for the coarse grain density matrix. Now, for this coarse grain density matrix, and then I can write a CFT formula for the area of that horizon. And for these purposes, this is a good coarse graining. For other purposes, maybe you want to use a different one. Partly because I want a formula. I want a CFT formula for that area. And partly because I think it gives a way of thinking about what role these wormholes play. You know, I think when we see non-factorizing solutions in gravity, it's very confusing what they're supposed to mean. And we should ask ourselves, like, what can I use this wormhole for? Okay, so this is something we can use this particular class of wormholes for. Okay, so we're going to match the wormholes, interpret this as a coarse grain density matrix. And by construction, this will have the correct entanglement spectrum. And in particular, it will have the correct entropy. I think of this as the derivation of the Ru-Takanagi formula in reverse. So in Ru-Takanagi, we're interested in the von Neumann entropy of the CFT. And we ask, what is the bulk quantity that calculates that von Neumann entropy? And Lefkowitz and Naldesena told us that it's the Ru-Takanagi formula. In this case, we're going in reverse. We have a bulk quantity that we're interested in, which is the area of the apparent horizon. And we ask the question, what is the CFT quantity that area is calculating? So that's the idea. Okay, so let me compare it to Engelhardt and Wall. They defined, so they argued that the entropy of the apparent horizon, including in these examples where it's also an extremal surface, is the simple entropy that matches where you maximize the entropy subject to some simple observables. And theirs is defined implicitly by an optimization procedure. In the boundary side, it's defined by a geometry. There's a gravitational construction for it, as was brought up in the discussion. Ours is designed to match the entanglement spectrum. It's less general in the sense that first of all, we require it to be an extremal surface. And second of all, step 2 on that previous slide is hard in general. You have some wormhole and you need to be able to write a CFT formula for it. But in the examples that I talked about, and I'll go through now, you can calculate it explicitly and write a CFT formula for that area. Okay. Okay.
I guess I'm a little confused. I mean, you just want the spectrum to agree. Can I just make some random state that has the right spectrum? And then say that's the density. I mean, it seems like it's more than that.
Well, that's what we're going to match. That's what we're going to do is we're going to find a density matrix that reproduces the wormhole. Yeah, I think it. Well, I don't know. What more do you want?
I'm just saying there could be many density matrices, and I can just you can calculate the spectrum with the wormhole. So let me just take a quantum mechanical system and with the right density matrix. So
this is going to be a CFT formula.
no, yeah, but I feel like then you're underselling it.
We could also do it with the state of the harmonic oscillator, right?
Well, that's not a CFT formula for the entropy.
It's a state that has the same entanglement spectrum. I mean, I feel like your construction is going to implicitly be better than what you're saying.
Right.
I mean, I think that's what, bothering us. It sounds more silly than it is, but we haven't understood why. If you tell it to us, then we'll be happy.
I'm going to give you a formula for the area of the apparent horizon. I think, yes, you could write a formula in the harmonic oscillator. You could like find something in the harmonic oscillator which was equal to the area of the apparent horizon. But I'm going to write the CFT formula for it, which I think is more than what you're asking for.
But I think that's not the answer, because even in the CFT, you could take some state that has absolutely nothing to do with and obtain and just construct by hand, by brute force that spectrum.
Yeah.
So you're probably doing something other than that.
Yeah, I agree. Doesn't your row prime match the outer wedge explicitly? Like not just
Rho bar?
row where.
No, it will not match all of the correlation functions in the outer wedge. It will not. Yeah, there's going to be a nice way of doing this, and maybe I can write the formula and we can pick it apart. Okay, so for the thin shells and the B states, so there's something special about these black holes, which is that they're locally eternal black holes, right? We got them just by patching together eternal black holes and possibly the vacuum region. You could add more shells and get more complicated solutions, which are locally eternal. And I think you could do something similar there. But for these locally eternal states, the answer that you get from the wormholes is the following. So let's take the original black hole and expand it in energy eigenstates. AN here is some UV sensitive expansion coefficient corresponding to that heavy operator, and tau naught is what you expect is just the obvious thing from the Euclidean evolution. The density matrix, this is a pure state, so the density matrix is just now a double sum of those eigenstates. And now we want to apply this strategy. First, we want to find the replica wormholes. Those are exactly, for these locally eternal solutions, the replica wormholes are the things I described in part 1. So we've already talked about the replica wormholes for this geometry. And now we need to find a density matrix that reproduces these wormholes. Now, that's ambiguous, but there's a very natural choice which does it. And in this example, the coarse grained density matrix that you get is simply the diagonal projection of the original density matrix. Okay, so you start with a pure state rho and n with which is a big matrix, and we're just going to define rho bar to be the projection onto the diagonal.
Sorry, Tom, the density matrix is always diagonal on some basis. So sorry, maybe I missed.
Sorry, the energy diagonal.
The energy, okay.
The energy diagonal.
Yeah.
Thank you. Yeah, we project onto the diagonal on the energy eigenbasis. Now we can match this to the wormholes. So matching this to the wormholes gives us a formula for this. This is the Euclidean evolution factor. This is some weighting function that you get by matching to the wormholes. I've written the answer here in the planar limit. Otherwise, it's a bit more complicated, and I have to add some notation here. But you can write the formula in general for this weighting function in terms of the action of the black hole. Cn squared is an unknown, randomly varying, erratically varying UV sensitive quantity, but everything has been defined in such a way that if you smear over some nearby states, that's approximately 1, so you can ignore it for calculating the spectrum. What's non-trivial about this formula is the k dependence when you calculate the replica partition function trace rho bar to the k. So when we take a kth power of this, what that'll do is it'll just raise this prefactor to the k, and you can see directly from this microscopic formula that there's going to be a k max when you do that, because there's an entropic enhancement in this sum from the number of states that you're summing over, but that doesn't pick up any k dependence. There's just one overall e to the s, even if you raise this to the k. These weighting factors are exponential suppressions and will get raised to the kth power. So eventually, if k is large enough, the semi-classical contribution will just disappear. Okay, and with this choice of coarse grained density matrix, you match the wormhole. Also note that k can be non-integer. And so even for the end of the world brains, this matches the wormhole. It matches the k dependence, including the fact that there's a k max. So also in CFT, for the end of the world brains, there's a maximum which is less than 2. And what we really wanted to get out of this was a CFT formula for the apparent horizon area. So now we can write that formula. By construction, the way we've done this, the area of the apparent horizon is going to be the von Neumann entropy of the coarse grained density matrix. And I've written it this way, just as the diagonal contributions to the ordinary formula for the von Neumann entropy. But we could plug in the previous slide, and then we'd have a fairly explicit CFT formula. It's not quite explicit because of those erratic coefficients, Cn squared, but those don't affect the semi-classical answer. This is all in the semi-classical approximation. Okay, so in this case, something nice happens, which is that this was already a thing. Okay, so there was already a proposal from condensed matter theorists that we should define the coarse grained density matrix of an isolated quantum system in a pure state to be this. So it was exactly this formula. In fact, we thought, what would be a good name for this quantity? Maybe the diagonal entropy. Let's Google it and see if anyone's used that. And turns out they used it, and it's this quantity, and they proposed it as a coarse grained entropy. So there's this thing called the diagonal entropy, which was proposed and studied in a number of papers on non-equilibrium quantum mechanics. The reason that they've advocated this definition of coarse-grained density matrix and entropy is because it has some nice properties. It obviously agrees with the ordinary entropy in stationary states. But furthermore, it satisfies thermodynamic laws. There's a first law if you assume ETH, the eigenstate thermalization hypothesis. And it satisfies something called a stochastic second law, which I won't go into, but I think it would be an interesting question what that means on the gravity side. Extremal surfaces, we don't usually think about extremal surfaces in gravity as having a second law because they just sit there. They don't time evolve. There's just one isolated extremal surface sitting there in space-time. Apparently this quantity that we've defined has a stochastic second law, and maybe there's some corresponding procedure that one can do on the gravity side to turn that into a second law in the bulk.
Well, apparent horizons evolve, right?
Yes, but this is not the special, okay, in this case, it happens to be apparent horizon, but this construction really used the fact that it was an extremal surface. Yeah, maybe this is related to the evolution of the apparent horizon, but that's certainly not obvious. In particular, this density matrix is time independent.
I mean, that's always, I guess that would, I mean, isn't that a little concerning? Like if you have some situation where you take your black hole and then you throw a big shell into it, then.
Would you like to add a massive particle?
I mean, Neda and I proved the second law for the apparent horizon. And if you combine that with this angular wall construction, you can always, chop out the outer wedge and then construct an actual quantum extremal surface behind it. You could sort of define a sequence of space-times.
Yes.
That are constructed from different parts of the apparent horizon and then apply what you're doing to quantum. Maybe that's related to that.
Yeah.
Yeah, thanks. Okay, so that's the coarse-grained density matrix for a locally eternal black hole. And now I'm going to add matter to it. Now, the kinds of matter that we know how to add is fairly limited for a reason I'll come to in a minute. But the one thing we do know how to do is to add massive particles at linear order and back reaction. And we should see something interesting happen, because if you add a particle behind the horizon, so now the red line is the shell making the black hole. The blue line is a particle. Okay, so the red line is spherically symmetric. The blue line is just a geodesic. So we're adding some massive probe particle and allowing it to back react the first order. But something interesting should happen, because if we add a particle behind the horizon, then the particle should get coarse grained away by any reasonable notion of coarse graining, I think. Whereas if we add a particle outside, then the particle should survive the coarse graining. That's what we expect intuitively, and that's what we're going to find. So how does that work when we go through this procedure? So the procedure starts with constructing the wormholes. For the case of the particle behind the horizon, so this is now the wormhole where the particle was behind the horizon. It basically just, you can think of it as part of the shell that made the black hole. There's no difference. It just is another contribution that's behind the horizon. It will go through the wormhole. So now instead of having the boundaries joined just by a thin shell, they're joined by a thin shell and by a probe particle. So there's really no difference here. You just absorb that into the definition of the shell. And so in that case, you end up getting the same formula at the end of the day, which is a diagonal projection of that density matrix.
Sorry, I'm not sure if this is contained in what you said, but like, for example, a thing that would be nice, although I don't know if it's true here, is if you have a situation where you have a particle that comes out of the past singularity, comes out of the black hole, kind of bounces off the boundary and goes back in, then you'd somehow like to see that the coarse grain entropy decreases and then increases. process. I can't quite tell if that's happening here or not.
This is the entropy of the apparent horizon. It's a single point in the middle of the diagram, and it's not changing in time. It's just,
Yeah,
it's just that
that's what's
point.
confusing me, is because I would have thought that this thing where a particle comes out and then goes.
I think
back
you're
in.
looking for the area of the apparent horizon as a function of time,
Yeah,
and that's just not what's being calculated here. It's the
Uh-huh.
area of the subdominant extremal surface at time 0.
yeah, okay.
I think you could perhaps treat situations like that by the strategy that Raphael was mentioning, where there's this procedure to sort of turn any apparent horizon into some other extremal surface.
Right, that was the
Then
way.
maybe
I
you could
understood
apply it
this.
to that extremal surface, but
Yeah, so
that's-
that prescription, I feel like it's going to give the right answer. I was just trying to understand if there's some way.
no, I'm saying you could combine the two.
Yeah,
In the sense that now you have an extremal surface there, and now you could use wormholes to branch around that extremal surface.
right, right.
But you can't just branch around the apparent horizon at any cross section. You can't construct those
No,
solutions. So you have to do
construct this
something
other thing,
complicated.
Following that strategy, you would have that new extremal surface that you get would be dominant, right? So
Yes.
you go back to somehow the previous case that we know about dominant extremal surfaces. So here, I think in your discussion, what
That's
was
true.
important was to give an interpretation for the subdominant extremal surface.
Well, okay, there's something I'm confused about. Maybe someone here knows the answer, but if you take those geometries, those Lorentzian geometries that are discussed that way, that are constructed that way, I'm not sure how many boundaries they have in Euclidean. In Lorentzian, they appear to have 2 boundaries, but I'm not sure whether it's more like the thermal field double, where they join in Euclidean, or whether it's more like the 2-boundary wormhole that I've discussed here. If it's more like the 2-boundary wormhole, then that would match. But I'm not sure which situation it is. You could imagine that.
It can be both, right? Like there's a Lorentzian
Picture where there's a 2-boundary wormhole, but then if you try to do Lefkowitz-Malesana, then you have something like what you said, right? I mean,
No, what I'm saying is if you don't do Lefkowitz-Malesana, just take that Lorentzian geometry that's constructed by that procedure
yes.
and evolve it into Euclidean. Do you expect to find 1 boundary or 2? I think it's not clear, but
Normally, the procedure of starting Euclidean and going to Lorentzian is well defined, but the other way around is.
yes,
Yeah.
yes, because we have to decide where the matter's going in Euclidean. I have a feeling it's going to hit the bound. I have a feeling that that you can think about it in a way where the matter hits the boundaries in Euclidean and prevents them from coming together. But it's just a guess. Yeah.
I mean, in general, there's just not a real Euclidean solution. I don't see why when we start with Lorentz, we should expect that to happen.
Yes. I don't know how to do it. Yeah. Okay, so if the particle is behind the horizon, it gets coarse grained away. That's good. Matches what we think of intuitively as coarse graining. If the particle is outside the horizon, then the wormholes look different. If the particle's outside, then the probes will just stay on the individual boundaries instead of going through the wormhole. And if you go through this strategy, this procedure that I described, then the coarse grained density matrix that you get is not the diagonal projection in the energy basis. It's something a bit more complicated. Here's a formula for it. But basically what it says in words is that to coarse grain this black hole, you should first strip off the operators O that create the particle. Then you should project onto the energy diagonal, and then you should put the particles, put those operators back. So this is a procedure that gives you the coarse grain density matrix that the wormholes agree with. Your question?
I was wondering if another way of explaining this is if you expand this, expand the initial state to some energy eigenbasis and treat all the ANs as random with some mean, distributed, let's say, and independent, then this is sort of like the average density matrix, the entropy of the average.
That's correct. That's correct. You take Yeah, that was the Gaussian average that I mentioned in the beginning. You expand in energy eigenstate, you take the Gaussian average. I didn't say it that way because I don't really know what that Gaussian average means. I don't think that those, yeah, I don't know what that means. It's a true mathematical procedure that you can take these things which are not Gaussian random variables and pretend that they are and get the wormhole.
So can I ask, you previously, even before this case, you just matched by computation. Is there some intuition why it matches?
I'm going to give some rough intuition in a minute. Yeah. Okay. So from the way that I've described this, so it was important that I took these locally eternal solutions and then added massive particles. There are other things that would be nice to be able to do, like to add full back reaction, or to add massless particles, or to just turn on general sources. That's not going to work, at least not in such a simple way. I don't know how to guess the coarse graining map because you know, a massless excitation is not localized in the inside or outside. So these words wouldn't even make sense if we tried to apply them to a massless excitation, including gravity itself. Okay, so if you add back reaction, then you have some gravitational excitations that are not localized, and I wouldn't know how to apply this procedure. So in that case, I don't have well, in that case, we don't know how to guess a formula or to calculate the coarse grain density matrix. A speculation is that I think that in that case, you may need to talk about projection in some kind of logical space. That you probably need to introduce a logical Hilbert space and do a projection there. That's just intuition based on the whole code story. Okay, let me make just a couple of concluding comments. The first is about the intuition for why you get this answer. And to explain this, I'm going to restate this main equation here in terms of holographic GHZ states. So the way I described it was that the wormhole is the replica density matrix, trace rho bar to the K. But another way you can describe it is that this is the overlap of a GHZ-like state. What I mean by a GHZ-like state is the following. You start with a black hole pure state, call that psi1 for single copy, and then construct a tensor product state with K copies, which you get just by raising the coefficients to the K. And it's called GHZ-like because, well, a GHZ state would, in quantum mechanics, would just not have this coefficient here. That's the definition of a GHZ state. And this has some weighting function, so I call it GHZ-like. Now, this is funny. So this is just a true formula. You know, I've just rearranged the bras and kets in the calculation of this trace rho bar to the K to reinterpret them as this overlap. So this is just a obviously true fact, but I think it has a nice picture for it. Now, people will maybe object that everyone knows you can't study GHZ-like states or GHZ states, GHZ entanglement holographically, because GHZ states violate the entropy inequalities of the Ruta-Kanagi formula. But there's a loophole, which is that if you cut the boundary theory in a way that the boundary spatial slices, the boundary spatial slice can be extended to a bulk spatial slice, then you can apply the Ruta-Kanagi formula and all these entropy inequalities. But if you cut the boundary in a way that there is no extension into the bulk, then those entropy inequalities don't apply. You're not allowed to use the Ruta-Kanagi formula in this way. And I think what's going on here is that these GHZ-like states are associated to these sort of windmill geometries where you take various segments on the boundary and merge them in the middle. Now, this picture is just a this picture is just a schematic. We don't know how to say calculate the wave function of this state, but we do know how to calculate overlaps of this state with the other half of the windmill. We just put in the other half of the windmill, and then we can calculate it. And this has a very natural. So here you can see naturally why it's a diagonal projection. So the idea is that when you calculate a coarse-grained replica partition function, you want to do this diagonal projection, and that in order to implement the diagonal projection, you should glue together the different boundaries by imposing a topological constraint in the bulk. So for example, like the state running here and the state running here in the CFT can be joined by a spatial slice. So they're related by some Hamiltonian constraint in the bulk, and that correlates the two sides. But of course, we can also draw a spatial slice that goes like this and correlates those two. So you get this many-party entanglement structure from this picture. And I think this is worth thinking about more, because we can study more general types of entanglement using AdS CFT if we understand how to do this in more detail. Okay. In my last slide, I want to make an experimental prediction. I'm only half joking here. So this same cut and glue procedure, I discussed black holes in AdS, but the same thing works in flat space. There's any time that you have a locally eternal black hole solution, you can apply this and construct a replica solution. There will be some maximum value of K, number of boundaries, but that's expected. So for example, you can apply this to the Oppenheimer-Snyder solution in asymptotically flat space. If you make the mass of the shell so large, sorry, this is a star actually, not a shell. If you make the mass of the star large enough that there's already a horizon at time 0, as opposed to the one we normally talk about in textbooks, in which a horizon forms later on. Using solutions like that, those sorts of solutions now allow you to do some of the things that have been done in JT gravity in realistic scenarios. Maybe you can even calculate some baryon number violating effects by taking to by interpreting those geometries as like the 10 to the 19 point function of some operators that violate a symmetry. Okay, let me conclude. Thank you.
Other questions for Tom? Is the coarse graining map a linear map?
I don't know. It's a good question. Yeah, another way of asking it is whether this thing that I called C is a quantum channel. And the answer is not the way I've described it. The way I've described it, you have to have some representation of the state. Not only do you have to have the density matrix, you have to represent it as being some outside operators acting on some microstate. And that goes into the definition of the coarse graining map. So the way I've described it, the answer is no, but it might be that representation is somehow unique. If that representation were unique, then I think it's likely that you could turn it into a quantum channel. We discussed some simple toy model where, like, if you suppose you had a Hilbert space that just had microstates where you could cleanly separate, where you had some set of microstates that were UV and some set of dressed microstates with some additional operators. If you could cleanly separate the microstates from the dressed microstates, then you can construct a linear quantum channel. But in the general case, like a CFT, we don't know how to do that.
Sorry, maybe I'm confused. I may be wrong, but if what we're literally doing is throwing away the off diagonal components of the density matrix, I thought that's like some dephasing channel or something.
Well, that was the right answer on one particular type of density matrix, which was the
Well,
first
okay, yeah, but so
example.
that I feel like maybe it's a channel. Yeah, I guess the general thing, I don't know.
Was
Just
it-
the rule of trying to match the wormhole. Yeah, okay.
yeah, the diagonal projection is definitely a channel.
Yeah.
But the general coarse graining map, so if you want to have a linear map, it needs to be defined on any input.
Yeah.
And it's not a diagonal projection on any input. It's only a diagonal projection on certain inputs.
Okay.
So
I wasn't thinking that complicated, but just literally, if you just take a superposition of two density matrices that you already described the procedure, and then you do the procedure for the superposition of those two density matrices.
yes, I think that is a linear map. If you restrict to the set of states that I talked about, then it acts as a linear map. That's the toy model that we talked about. I think, well, we didn't quite say it that way. I think that's true. I just think about it afterward.
More questions? If not, let's thank Tom again.
So